Okay, today we're going to cover more material on alternating series. So we'll start with an example to refresh our memories about alternating series, and then we will deal with the alternating series estimation theorem. So recall, for an alternating series, we have two types of convergence that we test for. Remember that there's a strong type of convergence, and then if we don't get the stronger type of convergence, we test for the weaker type of convergence. The stronger type of convergence is called absolute convergence, and the weaker is called conditional convergence. And the way to think of this is the idea that, so let's just run out some of these terms. So the first term, plug in n equals 1, so we get negative 1 squared, so it's a positive term. We get ln1 over 1, which is of course 0 because natural log of 1 is 0. But we're trying to identify the pattern here. When n is 2, we get negative 1 cubed, which is a minus 1, and then we'll get ln2 over 2. And then these will alternate in sign. And the idea, as usual, is does this sum converge? And remember, the question there, if we have only positive terms, deals with the terms racing to 0 in size fast enough for the sum to be finite. But the catch when you have these plus minus terms is that you're getting some cancellation in between pairs of terms. And that's what can account for this weaker type of convergence. So first, let's check for the stronger type. And anytime you're dealing with an alternating series, you always operate in this manner. So the first thing that we check for will be absolute convergence. And we generally call it the absolute convergence test to check for absolute convergence. And when we do that, we look at the sum of the absolute value of the terms. And the effect here is that it removes this minus 1 to the n plus 1. When we take the absolute value, those pluses or minus, plus 1s or minus 1s will always just be 1s. And so we have natural log n over n. And so in testing the convergence of this series, we are testing for the absolute convergence of the given series. And to think about this, we have the denominator, we have n, the numerator, we have ln of n. Well, for n bigger than 3, natural log of n is bigger than 1. So we actually can make an argument here. So maybe a graph will help us think of this. So if we think of y equals natural log of x, we know that natural log of 1 is 0. And then natural log of e is 1. So for x bigger than e, we have that natural log of x is bigger than 1. So for x larger than e, natural log of x is bigger than 1. And what this does is sets us up for our direct comparison test. So using this analysis here, we make the argument that natural log of n is bigger than 1 for n greater than or equal to 3. But then we can divide both sides of this inequality by n to get natural log of n over n is bigger than 1 over n. And we know that the sum from n from 1 to infinity of 1 over n diverges, as this is the famous harmonic series. So what we've done, if we recall how the direct comparison test works, is we've now found another series smaller than our given series, and this smaller series diverges, adds up to an infinite amount, which means our given sum must also diverge. So direct comparison tells us, here's another way we can write it, sum n equals 1 to infinity of natural log of n over n is bigger than the sum n equals 1 to infinity of 1 over n, and this diverges, which tells us that our sum, natural log of n over n, also diverges by direct comparison. And actually, to be technical, we should actually say we're starting these sums at 3, because that was where we got our direct comparison result. But of course, the first two terms won't matter, won't affect the convergence. So the sum, by throwing the first two terms in there, n equals 1 and n equals 2, we still get a series that adds to something infinite. So this is an argument, a formal argument, that this series, now remember what we were doing, this alternating series has failed the absolute convergence test. So this is what we conclude here. Our given series is not absolutely convergent. So the series that we were given has failed the stronger test. So we'll want to check for the weaker test. But before we mention that, it's also worth mentioning, there's another way you could have well, actually, this is the most natural way to do this one, is direct comparison. We'll leave it at that. What you want to do now that you have tested for the stronger convergence and failed to get it, we now test for the weaker convergence. And so remember, this is always the way you deal with an alternating series. The analogy, a good analogy, is you're testing for bench press strength in kind of an efficient way. So the first thing you do is you test for the stronger case, bench press 200 pounds. If the person can't do that, then we test for the weaker, or the 100-pound bench press. You don't want to do it the other way, because both a strong and a weak convergence will satisfy the weaker convergence criteria. So we always test for the strong convergence first with the absolute convergence test. If we get absolute convergence, we're done. If we don't, as we have in this example, we check for conditional convergence. And that's when we use what's called the alternating series test. And we check 3 criteria. And we go through them one at a time. So first, we check for the terms being bigger than 0. And this is true. Go back to our graph. Natural log of x is greater than 0 whenever x is bigger than 1, bigger than or equal to 1. Well, I should say, natural log of x is non-negative anytime x is greater than or equal to 1. So, of course, the denominator is always positive, so this gives us our terms being positive. The other criteria, well, the second piece, is to check that the terms are decreasing. And we should have a sense that this is going to happen because, remember, think of a race situation when n is going to infinity. Polynomial on the bottom versus log in the top. We remember that polynomials destroy logs in that race. That'll be an argument for the third criteria, that this term goes to 0. But it's also going to end up being the intuition that the terms will be decreasing because the denominator is outpacing the numerator. But we can show that, and the way we can show that is to borrow from Calc 1. So let's look at f of x is natural log of x over x. And if we can show that this is a decreasing function, then the terms in the series are decreasing because they're along for the ride. To show it's a decreasing function, we of course need to take its derivative. So let's recall we would want our quotient rule. So denominator, x, times the derivative of the numerator, 1 over x, minus the numerator, natural log of x, times the derivative of the denominator, 1, all over the denominator squared. Or 1 minus natural log of x over x squared. Now we made the argument that natural log of x is bigger than 1 for all n greater than or equal to 3. Well, if natural log of x is bigger than 1 for all n greater than or equal to 3, then subtract 1 from both sides of this inequality, and we see 0 is bigger than 1 minus, you subtract natural log of x from both sides of this inequality, and we get 1 minus natural log of x is negative, which means 1 minus natural log of x, divide that by x squared, which you can, because it's always going to be positive. That's less than 0 for all n bigger than or equal to 3. Thus, f is decreasing. Thus, natural log of n over n, which is f evaluated at n, is also decreasing. And the picture, anytime you have a function that's decreasing, and then your sequence actually sits on the function when x is the natural numbers, so these are your a's, say a1, a2, a3, the fact that the function is decreasing takes the terms in the series along for the ride. So we've used some differential calculus here to make an argument that these terms in these the sum are decreasing. So we have that. The third criteria for the alternating series test is to show that the limit of the terms as n goes to infinity is 0. So we check the limit as n goes to infinity of natural log n over n, and we recall that this gives an infinity over infinity indeterminate form if we try to directly evaluate, which means we can use L'Hopital's rule to argue derivative of the top over the derivative of the bottom. And we have the same limit, which is 0. So the three criteria for the alternating series test are satisfied. And this tells us that our original series, the sum of -1 to the n plus 1 times natural log n over n, converges conditionally. Which again is a weird type of convergence. Remember, we stated a theorem that said if your series converges conditionally, then you can actually find an arrangement to get it to converge to whatever value you want. But it's important to note, for a question like this, it's essential that you first test for the stronger convergence. If that test is satisfied, you're done. You don't have to test for the weaker. If the stronger test is not satisfied, we test for the weaker convergence, which we call conditional convergence, by checking these three criteria. Okay, so that's our an example, kind of a refresher on alternating series. Let's now look at the alternating series estimation theorem. This is a very important theorem. In particular, in this course, this theorem is going to be one of your best friends. Because remember, the goal is to get into representing a function, so a function of x, as a series that involves that variable x. That's where we're going with this. And the big result there is called Taylor's theorem. And what you'll do, a very common use of this series representation of a function, is to use a kth partial sum to approximate the function. So you take the first few terms to approximate the function. And of course, an approximation is only any good if you can say something about the error. And that's Taylor's theorem. That's the big result, is for the error. The alternating series estimation theorem will be very handy because it's easier to use than Taylor's theorem. And we will use this later on. And you'll be very happy that you know it because it makes things much easier. So let's go through the statement of the theorem. So here we have an alternating series. The bn's are greater than or equal to 0. Remember, we just write it that way so that these bn's are always greater than or equal to 0, and it's this -1 to the n plus 1 that ticks the sign -1, +1, -1, +1, on and off. So we have our alternating series. It's convergent, either type of convergence, and its sum is S. The kth partial sum is Sk, so sum of the first k terms. And that means we can write the total sum as the kth partial sum plus the remainder. And that remainder is just the rest of the terms, all the terms that you cut off after the kth partial sum. What this theorem says is that remainder, so solve for that remainder. You get Rk is S minus Sk. You can think of that as the error of the approximation of Sk using Sk to approximate S. There's your error. Well, your error is Rk. The error of that approximation, using the kth partial sum to approximate the whole sum, is less than or equal to b sub k plus 1. The way to think of that, what is bk plus 1? That's the first term that you leave out. The first of these bn's that you leave out when you form the kth partial sum. So this is the first term omitted from that kth partial sum. So this is telling us that the error, When you use the kth partial sum to approximate an alternating series, the error of that approximation is smaller than the size of the first term that you left out. You have to get rid of the -1. This is an absolute value. So the error in the size of the error is smaller than the size of the first term that you omit. That's your alternating series estimation theorem. So we can write it over here like that. So the error using SK to approximate S, the error, and this is how we'll often write it, is less than or equal to the size of the first omitted term. Now the geometry, or maybe I shouldn't say the geometry, the kind of number line analysis of it, we can actually see how this works. So let's say that here is S. So this value, this is the actual, and why don't we put a 0 here to give us a sense of where we are. This S is the actual value of the alternating series. This is what it actually converges to. And this passes, that means it passes the alternating series test. Whether it's conditionally convergent or absolutely convergent, it can still pass the weakest test for convergence. So that means what will happen is we'll have, so S1, maybe we'll use different colors. That's the first of the partial sums. That's just B1. So S1 is just the sum from n equals 1 to 1, which gives us plus 1 times B1. And we'll say B1, well, say S1, that first partial sum is over here. Okay, then we look at the second partial sum. Well, that's B1 minus B2. Because we have the minus because it's an alternating series, so the second term is negative. Now what's happening is the terms, remember, are decreasing, which means B2 is smaller than B1. B2 is positive, but it's smaller than B1. And you want to start thinking about this as a leapfrog thing. So S1 over here, to get to S2, we just take S1 and we subtract B1. Which means we're actually going to go back over here, but it's smaller than B1, so we leapfrog S, but we don't go all the way back to 0 where we started. We go, say, to here. If we do the third partial sum, well, we take that second partial sum, and then we add B3. But similarly, this will have us leapfrog S, but we won't go all the way back to S1. We leapfrog S again, and we get even closer. And you iterate this. You keep doing this, and because the terms are decreasing and approaching to 0, this leapfrogging routine will get you closer and closer, honing in on S. So you actually will converge to it. That's the idea of the convergence of the series. We actually haven't brought in the theorem. What the theorem says is, let's now focus on, let's look at this S3. So this B3 term, right? When we went from S2 to S3, we did that by adding the term B3. So B3, this distance here that we leapfrogged was B3. The error of our approximation, by definition, so if we're using S2 to approximate S, the error So the error using S2 to approximate S is S minus S2. That error is this distance. And what the alternating series estimation theorem is saying, simply put down here, is that this yellow bar is bigger than this black bar. So the reason why your error is always smaller than the size of the first term you left out is because the alternating series is having you do this leapfrog convergence. You're honing in on S, but you're jumping over it every time. And because you're leapfrogging it every time, your error of your approximation is smaller than the first term that you left out. So remember, this is the case where we're using this S2. If you're using S2 to approximate the whole sum, B3 is the first term that you left out. And so this is your error of your approximation, this black bar. This yellow bar is the error, is the size of the first term you left out. And again, the theorem is saying yellow bar is bigger than the black bar. So that's the intuition. That's the idea. And embedded in this is the idea of how you prove this theorem. But now let's see how you use this. So here we have an example of an alternating series. And this series does converge. And here, didn't quite finish the question. We're asked to approximate the series to within 0.001. And so this series does converge. The series converges absolutely. So if we check this with the absolute convergence test, 1 over 2 to the n times n factorial, that term races to 0 incredibly fast. And you can show that this series does converge. So assume that we've done that. Now we want to know, how can we approximate this to within 0.0001? And we immediately note that this is an alternating series. And so the alternating series estimation theorem told us that the size of our error is less than or equal to the first term omitted. And so what we want to then do is figure out what's the first term to omit. Now we know the theorem tells us that the first term omitted is bigger than or equal to the error. So we should point out this inequality is given by the theorem. We want the error to be smaller than 1 over 10,000. So what we do is force that by setting, we set this inequality. We force, if we choose the first term omitted to be less than or equal to 1 over 10,000, then by the theorem, because of this string of inequalities, we get what we want. We get that the error will be less than 1 over 10,000. So it all comes down to choosing the first term to omit to be small enough. So we focus on this inequality here. And for a question like this, we can quite simply set up a chart and then see, or maybe even better, let's just look at the denominator. And then we just run out different values of n. And eventually this thing will exceed 10,000. So when n equals 1, we get 2 to the 1 times 1 factorial, which is 2. When n is 2, we get 2 squared times 2 factorial, which is 2 cubed, or 8. When n is 3, we get 2 cubed times 3 factorial, which is 8 times 6, or 48. When n is 4, 2 to the 4th times 4 factorial. So that's what? 16 times 4 factorial is 4 times 3 is 12, times 2 is 24. And so we're continuing, when n is 5, we get 2 to the 5th times 5 factorial, which is 32 times, let's see, 24 times 5, 120, which is 3840. Oh, I forgot to write here. This was 384. And then when n is 6, 2 to the 6th times 6 factorial, that works out to be 46,080. So you can see that this term grows pretty quickly. But what we've noted is here, in the 6th term, we have 2 to the n times n factorial exceeding 10,000. So what that means, so since 2 to the 6th times 6 factorial is bigger than 10,000, cross multiply, we have 1 over 2 to the 6th times 6 factorial is less than 1 over 10,000. So what we've found is this is the first term to omit. We could have, of course, chosen a later term. We could omit the 7th term, the 8th term as the first term to omit, and that would work as well. But this is kind of the cheapest way to do it. If we omit this first term and we use the sum is approximated by, we go summing from n equals 0 to n equals 5. Of minus 1 to the n times 1 over 2 to the n factorial. Which, if we write it out, we left out n equals 0. Notice the sum does start at 0. When n is 0, we get minus 1 to the 0, which is 1, over 1. 2 to the 0 is 1. 0 factorial is defined as 1, so the first term is 1. And then after that, we're alternating where these terms here are the denominators. So we have 1 minus a half plus an eighth minus 1 over 48 plus 1 over 384 minus 1 over 3,840. And this, as an approximation to this series, has an accuracy within 1 over 10,000, as we were asked. And so this is the standard way that you use the alternating series estimation theorem. Your error always tells you your error is smaller than the first term you leave out. And then we force the first term left out to be small enough. And that gives us, via this string of inequalities, the error within the tolerance that we desire. And this will always work for an alternating series that's convergent. So it becomes a quest for the first term to omit. And again, this is a very important theorem to understand well, because this theorem will be extremely useful when we get into material on Taylor series.